Mathematicians are constantly writing things down. So in the pursuit of becoming more lazy, they're always trying to find shorter ways of writing down the same thing. For addition, some people found that if you had the same number, it would be way easier just to count how many times you saw that number, instead of having to write down 10 twos. This is where multiplication came in. It provides an effective way of conveying the same information without having to do all that hard writing. This worked great for most people, until a few people wanted to multiply lots of numbers. This became very problematic because they had already used x for multiplication, and some people had become even more lazy, like using parentheses, or even worse, just sticking a letter and a number together to indicate multiplication. This created a new problem for mathematicians. How do you show multiple multiplications in an effective way? Thus, the exponent. There was a lot of unused space around each number, so someone decided to do something about it. Nicolas Chequet was the first person to use it on the top part we call the exponent. Michael Sleep coined the phrase in 1544. Next up for the record came up with Robert Record, who came up with the terms squared and cubed. Let's talk about what different exponents actually mean. If we have 1 as our exponent, let's say we have the number 7, right? And we add 1 in our exponent slot right up here, we just get 1 of that number. So in this case, I just put 1, 7. Not a big deal. If I decide to up that number, it doesn't matter what the lower number is. But if I decide to up this to 2, there will be 2 of whatever number's down here. So 3 times 3. We call this 3 squared. Because if you look at it as a geometric structure, or on dealing with geometry, you notice that we have 1, 2, 3 by 1, 2, 3, and it creates a square, like this pancake here, which has 3 by 3 bananas. And you'll notice that 3 times 3 gives us 9, which is the amount of bananas that we have over there. So 3 squared. Now, what if you wanted to bring the number up one more time? Well, it's essentially like going up one more dimension. So let's say that you have 4 to the 3rd power, right? That would be 4 times 4 times 4, or 4 cubed. 4 cubed is essentially like stacking pancakes one on top of each other. There's 4 pancakes here, all stacked on each other. And if I add chocolate chips, I can get 1, 2, 3, 4 chocolate chips by 1, 2, 3, 4. And if we repeated that, we'd have a square, so 4 by 4, which is 16. And then if we stack it all together, we get 4 times that number. So 16 times 4 would give us our answer, or 4 cubed. For the purposes of this video, we want to talk about squares. Not like these. These are squares, right? Did I get this in the script right? These are squares, right? But these look like triangles. I guess they can make a square, and in fact they do. This is a square. It's called a tool, it's called a square. But we're not talking about these either. Instead, we want to focus on squares like this. This is just a twister board, isn't it? Yeah. Ooh, red. Which means we're talking about red squares. Squares are the exact same length long as they are wide. So if we wanted to write down the area as a length and a width, it would be the same. Squares are wonderful things. They're like a marriage. Joined together, they become one number. And now I pronounce you 2 and 2. You may now be squared. But what if you wanted to go the other direction? Like a divorce from yourself? You would have to split the number into identical parts, regardless whether they come out nice and neat on the end. We call the broken parts at the end square roots. Sometimes square roots work into nice numbers. Take the square root of 25, for example. Square root of 25 is just 5. Nice and easy, nice and simple. Square root of 16 is 4. But you're going to notice that there's a lot of numbers in between 16 and 25, but there's no whole numbers between 5 and 4. So what do you do with a number like the square root of 20? Well, it would probably be in between 5 and 4. So it would be somewhere about halfway in between, because 20 is about halfway in between 16 and 25. When you fully calculate it out, it will be equal to 4.472135 and it goes on and on and on forever. It's in between 4 and 5 because 4.5 is in between 4 and 5. 4.4 is right over here. 4.5 is exactly halfway, so it's a little bit below halfway. But this isn't an exact number. It's a never-ending decimal. We call these types of numbers irrational. Most of the time, we'll just leave the number in the square root format. So square root of 20 will still just be square root of 20, rather than trying to write a never-ending number. The main problem is if you find yourself stuck into a square root. The only way to leave is to find an identical number to yourself to escape. Even then, only one of you will survive. With a 50% survival rate, it's not a recommended operation to get a number. The advantage of a square root is when you do get a whole number out of it, you know that for certain that it comes in pairs. Pairs are delicious. That's right. That's the reason why I only brought one of them. So how do I get out of one of these square root thingies? Well, it's basically like being put in jail in Monopoly. There's only a couple ways to get out of it. So let's say that we have the wonderful number 12 right here. Yeah, okay, he's kind of cool. Anyway, he's going through and he's rolling along and he stops by the chance card and he happens to pick up the go directly to jail, do not pass go, do not collect $200. So of course, he's being the criminal he is, he's gonna continue walking through the entire place till he can get back to jail. He had a really good time with us. So, how does he get out? Well, in Monopoly, you either get a get out of jail free card or you roll doubles. But this is basically a square. So how do I get out of the square root thing? Well, let's first talk about what a square root is. A square root kind of looks like this, but typically in mathematics, we draw it like this, or something close to that. Now, let's say that we had our number 12, and she's stuck inside this square root. So how are we going to get her out of there? Well, we can actually split her up into her prime numbers. So let's split her up into her prime numbers. Now remember, we're still technically under a giant square root thing, so this square root extends all the way down, but we can still split it up inside. So let's take our number 4 over here, and the number 3, I think. Because 4 times 3 gives us 12. So this essentially becomes into a square root of 4 times 3. Now we can put a little times right there. Now this 4 can be broken down into even more parts. So we can actually move this 3 over, and we can break this 4 into a 2 and a 2. So let's put that 2 over here and another 2. So we're left with 2 times 2 times 3, which is great for us because that means that we have 2 of the exact same number and they can become a squared number. So 2 squared. Now here's the thing, that little square right here is basically a get out of jail free card. So this becomes 2 squared, and this get out of jail free card goes into this 2. So on the way out of the square root, this 2 over here can say, all right, I'm submitting my get out of jail free card and escape from the place. Sorry for the second 2. The 3, on the other hand, well, he's drawing a chance card that gets him a stuck in jail. So he'll be in jail for the rest of his time. So this is our answer. Our answer is 2 square root of 3. So we can use a square in exchange of this. Square roots can get even more complicated when we talk about negatives, but we'll save that for another video on the subject. Thank you for joining us on this episode of From A to B, and we hope to see you soon. Are we doing another episode? Wait a second, this is episode 2. Why are we filming this out of boredom? production schedules.